For this video, I investigated constant velocity using the equation of Newton's second law called the momentum principle. The equation is given as final velocity equals initial velocity plus the net force over the mass multiplied by the change in time, represented here by delta t, also known as the time step. The velocities are both measured in meters per second, the net force is in newtons, the mass is in kilograms, and the time is in seconds, all in accordance with SI units. The object I chose to film was a tennis ball, chosen for its uniform shape, size, and easily observable color. It was measured at approximately 6.7 centimeters in diameter, which in meters is given as 6.7 times 10 to the negative second power. This is the calibration stick I used, measured somewhere in the middle of the video in order to get the calibration correct. The plane I used has the ball traveling in the positive x direction, or to the right, beginning at the origin. Because my ball began from rest, its initial velocity was 0 at a time also equal to 0 seconds. A small impulse was given, and the ball began to roll across the table as shown here. The clip was shortened to only 0.75 seconds from 3 seconds, so that the initial impulse was not included in the frames analyzed, and because motion tends to change less over small intervals, helping to keep the velocity constant in my calculations. These are the values given by Tracker, and this is the graph of this data. From these observations, I developed a computational model of the motion in Python, shown in the code here. The mass was changed to reflect the mass of the object, shown here, which was measured at 57 grams or 0.057 kilograms. The initial position and velocity calculated by Tracker were not completely zero as I'd originally anticipated, but because Tracker has calculated this in its calculations and I accounted for it in the model, it doesn't really affect the constant velocity. The time step delta t was chosen small to give better results and help give a graph with many data points to study. The time was changed to the length of the video clip. The force was assumed to be a zero net force due to the constant velocity motion. And the velocity and position equations were input into the code in order to run successive calculations to model motion. Here's the initial equation that I showed in the first part of the video that describes the final velocity, which updates constantly to do the successive calculations with the final velocity of the current run as the initial velocity of the run afterwards. And the position updates with that same velocity and delta t in order to give the new position to create a graph of the motion constantly as it updates. Running code gives this graph, which, as you can see, goes in the positive x direction at a constant rate. After both tests were run, the data received was placed on one graph, shown here. As you can see, the experimental and model graphs line up almost perfectly. The reason they are not exactly the same is due to human error in ball position, how level a table may have been, and because the code does not account for the force of friction. Had this been a frictionless surface, the two lines would be virtually equal. Despite the friction being ignored, Because the two graphs are close, I believe that this is still a valid model of constant velocity motion.